So I get to introduce Professor Ananya Ipsita. Dr. Ipsita holds a Ph.D. in mechanical engineering from Purdue University, where her research lies at the intersection of smart manufacturing, human-centered computing, immersive technologies, and engineering education. She develops interactive systems that integrate augmented reality, virtual reality, Internet of Things, and artificial intelligence to support workforce development and hands-on experiential learning in manufacturing. Her prior work includes designing accessible AR/VR simulators, AI-assisted authoring tools, and AR-IoT-based learning curricula and platforms for K-12 and undergraduate students. This seminar will focus on workforce development and manufacturing through smart and immersive technologies, addressing the skills gaps in manufacturing by exploring the following strategies. 1, developing outcome-aligned immersive training content. 2, enabling content creation by subject matter experts. And 3, embedding multimodal assessment into training systems. The goal is to equip diverse learners with advanced manufacturing skills and democratize access to manufacturing education. So please join me in welcoming Dr. Ipsita.
Thank you so much. Thank you so much, Dr. James, for this lovely introduction. Good afternoon, everyone. Welcome to this seminar on workforce development for manufacturing using smart immersive technology. Let me just add a couple of stuff to what Dr. James just shared with you. I did my Ph.D. in mechanical engineering from Purdue University, and my focus of my thesis was to enhance accessibility of immersive training in manufacturing. My current research interests are shown in this slide. My primary focus is in the field of human-computer interaction, with a special emphasis on workforce development in smart manufacturing. I utilize tools such as immersive technology that includes augmented reality, virtual reality, or mixed reality, Internet of Things, robotics, automation, and engineering education as well. Here is a brief roadmap of today's seminar. First, I will start with providing a quick background and followed by a motivation for my research. And then I'll dive deep into 3 research topics, where I will first introduce you to some prior research that I conducted in those topics, followed by some research possibilities that I'll open in those areas. I suppose this talk will last for like 45 minutes and like providing a 15 minutes time gap for Q&A and open discussion with you, where I would love to hear your insights about the research or anything that you can find interesting from the talk. Now let's see what is manufacturing. Like you must be already familiar with this topic, but it's a well-known process where we start with a raw material and then produce a processed product using machinery, tool, a wide range of manufacturing processes, including energy and labor. Speaking of which, this field is like utilized across a lot of industries, some of them being food, paper, electronics, electrical, transportation, so on and so forth. Now let's have a quick glance at the importance of manufacturing. And this is the data collected from some labor stats from 2023-2024. And it seems manufacturing contributes to about 10% of the national economy, and almost about 8% of the workforce is employed in this sector. Now, despite the significance of manufacturing, there is presently a skill gap in the industry, which is resulting from a lot of factors. Some of them being rapid technological advancements from automation and technology, then changing job requirements and market demands, and simultaneously, there are limitations in the current educational systems, which is unable to meet this skill gap. So therefore, there is clearly a need to address the skills gap, and we will be exploring mixed reality as a medium to entertain such skilling efforts. Now let's understand what mixed reality is. Okay, now the image on the right top, you can see the mixed reality is basically a spectrum, where on the left lies the physical world and on the right lies the digital world. Towards the left, there is more of a physical presence, and that comes under the domain of augmented reality. But on the right, there is more of a virtual presence, and that comes under the domain of virtual reality. And it combinedly forms a mixed reality spectrum. In other words, mixed reality is nothing but a computer-generated simulation, and it replaces users' perception from the real world to a completely different or similar replica of the physical world. Now, because of the different benefits that this immersive technology provides, it has been found quite useful in the field of skill training and learning. Some of the benefits are listed here. It provides hands-on experiences to learners using spatial and embodied interactions. It has been found effective in case of constraints such as where there is high cost for equipment setup, or there is high cost for instructor time. So it's found effective in those kind of constraints. It's also found effective in enhancing knowledge retention and reducing errors, as well as increasing user satisfaction and experience as compared to 2D alternatives such as video or paper-based training methods. Now, with that background, I will dive deep into the three research topics that are listed here. The first one will be focusing on how can we build and design learning environments using such kind of technology by incorporating principles from learning sciences. The topic 2 will go deep into creating immersive content by subject matter experts without needing technical expertise. Topic 3 will dive deep into how can we increase accessibility to advanced manufacturing skills such as robotics or Internet of Things, which are kind of advanced, which are like the future of manufacturing. And I would go deep into that like in the research topic 3, but how can we increase accessibility using XR-based interactions? Okay, let's talk about research topic 1, which will mostly focus on design of effective learning environments using mixed reality. In my prior research, my work has been focused on welding. Like welding is a skill that is widely utilized in the field of manufacturing, and it has been shown by American Welding Society that almost about 50% of manufactured products require some skill set of welders. Despite its significance, there is an estimated shortage of skilled welders, as reported by American Welding Society. Therefore, our prior research was focused on utilizing an outcome-oriented design and combining the benefits that virtual reality training provides to facilitate faster skilling of welders by creating a low-cost welding curriculum. Now, here I will talk about what was the theory or the principles that guided us towards the design of the curriculum. We adopted something called as a backward design principle from learning sciences, which starts with collaboration with the subject matter experts. So we collaborated with subject matter experts from welding training organizations and industry to lay out a list of learning outcomes. Learning outcomes are nothing but what do we want our learners to achieve at the end of the training. Now, based on that, we laid out the different learning objectives that would lay the foundation of the welding simulator. Next, we backward tracked the skills and assessment that would prove as an acceptable evidence that the learners is learning whatever we want them to learn correctly or not. Now, the next step is planning the learning activities based on the prior research. So we decide what content should we build in our welding simulator so that the learners could achieve those skills. And finally, the curriculum would be the result of laying out the learning activities in a gradually scaffolded manner so that the learners is introduced to gradually, to increasingly complex concepts as they progress through the simulator. Now, this was a result of our research. We designed a welding curriculum with 5 modules. The first 3 modules were primarily focused on welding basics, which covered the topics such as safety, equipment setup, and maintenance. And the next two modules were more hands-on in nature, where the users could practice welding on different joints and positions, and also like practice their skill and apply their skill in authentic environments. We utilize a truck tailgate a model from a local company, and we provided learner with the environment to apply the skills in an authentic environment. Now, these are some guidelines that laid the foundation for the development of the learning activities. We designed realistic assets in the form of virtual models and interactions using 3D modeling softwares or collected resources from online sources as well. Interactive video tutorials and guided activities, including avatar demonstrations, were utilized to guide the learners and present them with necessary activity to practice their skills. Data evaluation techniques were also utilized to assess the learners at suitable checkpoints to basically assess if they're learning the skills correctly or not before they're moving on to more complex materials. We designed a visual haptic guidance mechanism so that the learner could actually hold a physical welding gun when they are practicing virtual welding. So as you can see in the figure, so there is like a 3D mount which is mounted on top of the physical welding gun, and that can hold the Oculus controller. So holding that in the virtual, during the virtual welding, provided the learner with realistic feeling of being able to practice virtual welding in a real world. Finally, we also collected 360-degree video renderings from local companies and rendered it in the virtual environment, which could provide personalized training environments to the learners. With that, here are some videos which show a minimum viable prototype that we developed to test the usability of our welding simulator. The first video over here shows the safety module where users can look around and identify personal protective equipment in the welding workplace environment. The second video over here shows a guided activity where the user can perform wire change on a virtual welding machine. The third activity shows how the users can practice virtual welding on a T-joint. Using the minimum viable prototype that we developed during the research, we performed a few studies. One of them is we performed a comparative study between a VR and video training group, which showed results in favor of the VR training. It showed that VR training enhanced students' performance and experience as compared to 2D-based training methods. It also achieved higher accuracy and reduced errors as compared to 2D video-based training. Another study compared the effect of haptics while performing virtual welding. It was observed that accuracy as well as user experience. When I say user experience, it was basically the feedback that we collected from users. How closely can they relate the virtual activity to the physical activity? It was found that these parameters improved with the use of the real welding gun as compared to the default Oculus controllers, which suggests that there is a need to design hardware to suit the requirements of the skills that the learner is learning using the virtual simulator, rather than fitting a one-size-fits-all hardware to meet all needs. So with that, I would like to open some possibilities for future research that could be explored further in this area. The theories that we utilize to design the welding simulator can be utilized across other manufacturing domains such as assembly training or riveting and many other manufacturing processes. Second, there are different tools and interactions utilized across different manufacturing processes. So this could be an interesting topic as well to explore further, as in how do these haptics affect the skill transfer for a learner. let's now move on to the next research topic, which will focus on enhancing accessibility for creating training content without the need of technical expertise. Yes.
Sorry to interrupt you. Is the welding only for spot welding, or it can be used like this training? Is it only for spot welding or continuous?
We designed it for MIG, metal inert gas welding, so it's continuous welding. So yeah. So the motivation of the research topic too stems from the barriers in adopting extended reality or mixed reality for manufacturing training. One of the major barriers is lack of accessible methods for authoring. When I say authoring, it means creating content for my instruction. So it's often found that creating content for immersive skill training requires a lot of technical expertise, which the subject matters do not typically have. So in our prior research, we developed a few tools to reduce such authoring barriers. One of them was called VR from X. Let me walk you through the different stages of this system. The process starts with a welding expert wanting to create the virtual simulation of their welding station. They use a handheld scanner or a consumer level scanner to scan their physical welding station. This scan can be stored across many devices in form of a digital point cloud. The experts can then interact with this point cloud to create virtual objects. The next step would be adding interactive functionalities to make these virtual objects interactive. And finally, the scene is ready for virtual welding. And you can imagine such scenes can be used for virtual skill training as well. So here is a video that shows the different features of the system. So in the first session, you can see the user interacting with a point cloud to retrieve a 3D model of a welding machine. In the second video here, you can see like the user attaching interactive functionalities, in this case, a welding flame to the welding gun. And in the third case, you can see a user finally practicing the welding in a virtual setup that they created. To confirm the usability of such system, we conducted a user study where we tried to examine the effect of technical expertise on the authoring, on the authoring experience provided by VR from X. So I want to mention here that all users in this study had prior hands-on experience with welding. And it was found that no significant difference was found between the performance of the two user groups. And they found that the system was easy to use and it was quite effective in developing basic simulations for the welding training. Here are some snapshots from the simulators that the users created during the user study. Now with that, I would like to talk about a few research possibilities that could be further explored in this area. So one modality that we utilized in the prior research was a sketching modality where user could sketch in mid-air or select points in point cloud. But other modalities that could be explored further would be head movements, hand movements, or even speech gestures could be explored to improve user experience during such in-situ authoring. And such workflows can also be utilized in mixed reality environments for smart manufacturing. For example, here you can see a user sending a model for 3D printing remotely and the model being printed using a 3D printer. And it can also be used for human-robot collaboration on the right, where you can see the user is like authoring checkpoints, and then you would see a robot following the checkpoints and performing activities on a real world. So it can be adopted across mixed reality environments for other purposes as well, beyond skill training and learning. Okay, now let's talk. I'll talk about some other authoring tools that we also explored, which allows experts to author outcome-oriented lesson plans. For example, during creating a lesson plan for our class, we normally take into consideration the experience that the students have from before, as well as the objectives that we want as a result of the learning, right? So we change our lesson plans to tailor to the content to meet our class requirements. Now, a commonly used method that works best in such cases is by utilizing these instructional phases, which are color-coded here, like there is introduction, followed by presentation, followed by practice and application. So let me explain these instructional phases a little bit in more detail. Introduction is basically introducing a particular topic to the student. Then presentation provides sufficient background material to learn about that topic. Then practice activities provide assessment exercises to the learners to basically practice that skill, followed by application where the user can apply the learned skill in some authentic environments. When I say authentic, it means like close to real environments. So with that background, we develop something called as flow train IVR, which allows subject matter experts to author lesson plans. And again, we put a lot of emphasis on the subject matter experts. So the process starts with the experts collaborating with the VR developers using backward design or other principles from learning sciences. So it starts with this collaboration to develop the learning activities which can be grouped under the instructional phases of introduction or presentation or practice and application. In the next step, the experts can utilize these learning activities to author lesson plans in form of instructional sequences to cater to their class requirements. This slide shows the three most important features of the design. First, the learning activities are created and grouped under the 4 instructional phases. Again, these are color-coded. You can see there are instructional phases for introduction, presentation, practice, and application. Next, the experts can use these activities in any order to create instructional sequences using a graph-based editor. Finally, these lesson plans could be imported to the front end, where the experts could test and evaluate that the lesson plan is meeting their class requirements or not. We conducted a 3-session user study where we provided this system to welding users. And the users were asked to design lesson plans in each session, where each session had increasingly complex class requirements. And the results indicated that the users were able to flexibly author lesson plans based on varying skill requirements. So this confirmed the usability of such systems. However, one thing that was noted as a limitation of such system was with increasing learning activities, planning could get cumbersome. In such cases, we envision that utilizing large language models can improve the planning process. So we utilize LLM in the next step to update the system workflow design. So again, like the emphasis is still on the subject matter experts, and then the first process remains the same, where they collaborate with VR developers to create the learning activities. But in the next step, we add LLM support to help experts author their lesson plans. Now here is a video that shows the updated version of the graph editor that user can provide prompts to the LLMs, and the LLM can create an instructional sequence for them, which could later be modified by the experts. We performed a comparative study of the 2 systems with LLM support and without LLM support, and the results were clearly in favor of the system with LLM support. It was found that the LLM support could improve the user experience and reduce the workload and timing required for the authoring process. Now, with that, I would like to talk about some possible research directions that could be further explored in this area. Now, talking about conventional manufacturing processes, say welding or riveting or assembly, it requires a ton of spatial activities, right? Like when a novice is learning manufacturing skill in a workplace environment, the instructors typically tend to observe their movement and provide provide feedback based on their direct observations, right? So this could be replicated in a similar, in a virtual setup as well, where we can ask, where we can capture the key performance indicators from the expert's actions, and using those key performance indicators later assess the learner's progress. So yeah, so this is basically building and embedding observation and assessment within the XR training. Now let's move on to the last research topic, which will explore increasing accessibility to advanced manufacturing skills using XR-based interactions. Before that, I would like to bring your attention to the emerging trends in manufacturing. Contrast to like the conventional manufacturing processes like welding or assembly, which rely more on hands-on or spatial processes. Some of the emerging trends in manufacturing, or we call it Industry 4.0 or 5.0, some of the emerging trends, they seem to be more interdisciplinary and data-driven in nature. And one of the emerging trends is Internet of Things, which is revolutionizing manufacturing sector by improving the connectivity between man and machine. Now, it is important to expose such skills to younger generations to enhance their interest in STEM. So with that background, I would like to introduce some prior research that we conducted in this area. And our goal was to design a kit to expose Internet of Things to IoT high school students using augmented reality, design, and prototyping. Some of the design goals that we laid out for our kit are shown here. Some of them were to keep it low cost and engaging, and then allowing simple interactions, and while allowing them to explore multiple pathways as well. Now, here is a brief overview of the storytelling kit that we designed. It has three major applications. The first one is Device Maker, which allows students to build and prototype smart physical devices that could be a part of their stories. Next is Event Maker, that will be helpful in creating events between virtual characters and physical devices to create the events for their stories. And finally, we have something called a Story Maker, which allows them to bring their stories to life using augmented reality and the physical digital interactions. Now, let's look at these three applications in a little bit more detail. The first one is Device Maker. It provides an electronic library to the students where they can use like simple plug and play instructions to connect their boards to different electronic components such as sensors and actuators to sense and perform actions on the environment. The Device Maker also supports a block-based programming interface where young students who do not have a lot of prior programming knowledge, they can use like drag and drop based interactions to code their physical prototypes. Next is the Event Maker application where users are provided with an interface to connect the physical and the digital characters to create interactions or the events. Finally, this is the Story Maker application where a user can select the events to tell their stories using augmented reality. Now, here is a funny video that we recorded from our user study. Here you can see a user designing a virtual golfing experience. On the right, you can see the Story Maker interface that another user is carrying. As soon as the ball reaches the target, the physical windmill over here, it starts running, and also there is a virtual dragon which you can see on the phone-based interface that comes on the way as an obstacle. So this is a part of the collaborative experience and as well as like the storytelling experience that we encountered during our user study. Now these are some devices that students created, like the smart devices that students created during the user study. The study results indicated an increase in user experience and interest towards such technology as well. Now with that, I would briefly like to mention some research possibilities that could be further explored in this area. An interesting observation that was found was kits like Storymaker supports collaborative learning among users. Now, groups with larger sizes over here, there is a column called group size. If you can see the group size, the higher the group size, it's normally the case that the higher the number of physical virtual interactions. And the higher the number of physical virtual interactions, that is more flexibility to make your stories more creative. So it would be interesting to explore how to support and assess collaborative learning in such situations. Now, as a summary, I would like to finish my presentation with this slide. The seminar focused on the workforce development in manufacturing using mixed reality. The goal is to increase accessibility of learning for current employees through supporting work-based learning, for upskilling and reskilling, and as well as pre-skilling future employees towards the future of manufacturing. So here are some references that I used during the seminar. Thank you all for attending. Now I'm open for any questions that you may have. Yeah.
So great work.
Thank you.
So much for the presentation. So when you run the LLM model,
Mhm.
you run this on the fly, in real time, and you
Yes.
use like ChatGPT in the backbone of
Yeah.
the simulation?
Yeah, we used the GPT server and it was runtime. Yeah.
I was going to ask about that as well.
Mhm.
Do you have an example of like a prompt?
Yeah.
Fed into it? Because you give it gives you back very specific
Mhm.
steps to follow.
Yeah.
So did you train it on anything outside?
Yes, we actually provided it with some description of what are the learning activities we have. For example, we categorize the learning activities under the 4 instructional phases: introduction. So we provided a short description for each activity and fine-tuned the model, I would say. And then when we give the prompt, it could understand what are the learning activities are available, and based on that, it could generate an instructional sequence. Yeah. Mhm.
So back to the first,
Prompt.
you might, you show a prompt.
Yeah, for sure. I think I might have, it might be there in the video that I have in this slide. So here, here the prompt says, let me just zoom it. The student needs to be able to learn about T-joint welding. Yeah, and based on that, like if you add more details over there, it creates a set of learning objectives. Again, it's like we try to incorporate the principles of backward design during the authoring process, which lays out like what would be the learning objectives and what would be the criteria. And based on that, it creates the sequence of the learning activities or the lesson plan. So yeah, like.
Does it know, like it's able to tell you how to use your virtual welder? Like, does it know the buttons and things like that?
No, it does not know in that detail. So it's like a very high level description of the learning activity that we have. Yeah.
Yeah, more technical, okay?
Mhm.
So when you build the environment for welding, so what do you actually need? So it seems like you're using Unity to build the environment.
Mhm.
So Unity have like a lot of environment to integrate. So, so what is the technical core part of when you build a curriculum? Like what do you need? Like you build a class for continuous welding, right?
Mhm.
So you have a tools for Unity, and then you add it maybe later on for the LLM model.
Mhm.
So what do you actually need to build to complete an environment for teaching us how to do spot welding or continuous welding or maybe other applications?
Yeah.
So where is the technical part?
Are you talking about like the technical
Like
novelty of?
coding,
Okay.
Okay.
So it depends. Like for example, my first system was more of a uh, like an educational work where we combine the well established principles from learning sciences. Like for example, we utilize the backward design model, which is like widely followed for designing effective curriculums. So the novelty was more on the educational perspective: how can we build effective training content. But like if you ask me about the technical novelty in the system that we design, I would say like the way we designed the interactions, for example, there was a mechanism for providing visual haptic guidance during performing virtual welding. So what we did was like we obtained some key performance indicator based on our discussion with welding training experts, where they said like these are some parameters that you need to keep track when you are assessing the learner for continuous welding. For example, your travel angle, work angle, travel speed, and like contact to tip distance, they should be within these ranges. So we had to capture those in real time and then compare that against the standard ranges to see and assess whether the learner is practicing it correctly or not.
So this set of parameters or the guidelines
Mhm.
to create a well-defined curriculum for spot welding.
Mhm.
You get this information from users, from experts, but then where is the implementation part? Like, how do you implement those parameters within Unity? Like, do you need
Okay.
lots of work to integrate those using coding, or like how do you actually implement them?
Okay, so Unity uses a code editor which is called Visual Studio, and it's like Unity has a built-in physics engine that you can use to create your good game elements, to create your interactions within the environment that you're building. But sometimes it's not enough.
Right.
You have to rely upon other sources such as Blender and like other 3D modeling softwares and environments, which can take quite some time.
So,
But
so in other words, you build part of this environment using additional tools or libraries.
yes.
Like a Blender, for example, as you
Yeah.
mentioned.
Mhm.
And then you take this one and you embed this one into the Unity,
Yes.
or you just drag and drop.
We have
It's beyond this, right?
Yeah, it's beyond drag and drop. It's not that accessible. So yeah, a part of my research was also trying to reduce those authoring barriers. Like how can we enable subject matter experts who do not have expertise in Unity or other things? Like how can they build the training content for their classrooms? So a part of it, but I think still there is a long way to go. Yeah.
Is there any plan for welding under extreme conditions, like maybe underwater welding or things like that? Because this is very important.
Mhm.
Like I know the price hour for underwater welder is
Yeah.
very expensive.
Mm.
So is there any plan to extend this?
I think that will require additional research. For example, the learning parameters would vary based on like the type of environment that you're performing welding. Ours was more basic kind of welding that we try to that we design for our simulator. But yeah, for underwater, that could be an interesting topic to research as well. Yeah.
I know you have talked to a lot of experts for
Mhm.
developing that. But question, do you have any feedback from people who didn't know anything from welding, and then after this training go to field and do welding, and give feedback how different this was with that? Do you have any feedback on that as well?
Yeah, that is a great question. We actually plan to do some long-term study to actually evaluate whether this leads to the development of muscle memory in novice welders or not, which unfortunately we could not do that with the limited time that we have. But that's a great question, and some studies they actually have measured the effectiveness of welding or like immersive reality, and it has been found to be effective. But yeah, we did not do it in our case. Yeah.
Following the extended applications, I was thinking about surgical training.
Mhm.
So if you wanted to change the application, is it adaptable to other applications like instead of welding and joints, you
Mhm.
just use the soft tissue dynamics, or is it adaptable or just?
Yeah, great question. I would say the theories or the background principles that we have utilized in the research could be scaled across other domains, but there has to be some groundwork that needs to get done to be to able to reach that particular point where we can use the content for training and learning. So, for example, we need to create assets, we need to create those interactions and create that database or other things, and yeah. Sorry. Go
My
ahead.
question is,
Mm.
taking it to how good is the simulation-based training compared to real-life training? So that you're trying to get as close as you can to real-life training. So there is this gap between the physics that Unity can represent from reality. So it's not all the way there. Maybe, for example, this underwater building situation, maybe the physics is just not in Unity. So you will have to build that, right? So is there a way to say what is good enough in the simulation training in terms of the gap between the physics of the model versus real physics?
Yeah, great question. I think again, the motivation is not to replace the in-person training, but make some alternatives to already existing training alternatives, such as 2D video-based training methods, where students can gain a better prior hands-on before they go to the real world for practicing. Coming back to your question, uh, it's there, but it's still not there. Replicating the physical into completely into a perfectly virtual scenario is ideal, but in our case, the simulations that we designed could provide learners with a an entry level experience for them to get interested in that skill or to know some things about that skill before they go to the actual workplace environment and practice the skill to develop the real muscle memory that they need to learn in the trade.
Hi. I think your research is very interesting.
Thanks.
I have two questions. One, kind of building on his question about how you develop the Unity workspace. So you mentioned that you were testing large language models for the learning side of it. Do you think large language models either now or in the near future could be used to generate whatever materials or virtual objects? Do you think they could generate a virtual Unity environment based on a picture of your surroundings?
Great question. And I think the world is headed there. For example, right now I have come across papers where they could provide inputs as some text, and then the AI model could generate the 3D model based on the coordinates or the text that is describing it. So I think we are getting there. There are more efforts. But yeah, it's still not there.
Okay.
Yeah.
And then thank you. My second question was more on the first research you were showing. Did you measure their survey or just the user experience? Did you measure levels of exhaustion from using virtual reality as compared to watching videos online during the training?
Great question. So there is this questionnaire which is commonly used to determine the mental workload that the learner is facing during interacting with a system. It's called NASA TLX. At that point, we did something called as a virtual reality sickness questionnaire, which was the objective was to check if the person is feeling motion sickness inside, during the simulation. But we did not do the NASA TLX for the first experiment. But the motion sickness one indicated favorable results.
Okay.
Yeah.
I guess to follow up on that, what was the population you were studying? Was it mostly students, college age students, who were using the VR?
Each study was different. For the first study, I could bring up that slide. For this training, it was all welding novices. They did not have prior experience in welding. So we wanted to compare the effectiveness of VR versus video training.
Did you ask their prior experience using VR?
Yes, we did.
Did they have any at all? Or?
So we had a scale from 0 to 5, and I don't remember on the top of my head, but it was low, less than 2 or something. Yeah.
Thank you. I think that's all my questions.
Okay, thank you.
I have a question. My question is, did you perform any kind of time complexity analysis when you pass prompt to the ChatGPT, how much time it's spending based on the prompt size? And the other question is related to did you have any evaluation metric where you can tell how good is your planning. I heard that LLMs are not good at planning tasks, and we need to develop any mechanism to evaluate the planning part.
Great question, but we did not do such analysis. But that could be a future scope of research. Yeah.
Okay. And
We-
time complexity analysis,
Uh,
like how much time it's spending on planning tasks.
For the AI model, we did not capture the timing. We were more interested to evaluate the usability of the system from a user perspective. Like we collected the timings that, for example, so in this particular slide, although this is not the comparative study, but we did measure something like this for the second study also, like where we ran the comparative study between the system with LLM support versus the system without LLM support, and we saw that like we captured the timings that users require to create and author sequences and lesson plans, but we did not capture the timing that the AI model took to generate the sequences. But that could be a scope of future research as well. Yeah. Mhm. Yeah.
Another question.
Mhm.
How much content would you say there is in your virtual welding training? Is it something equivalent to a course here, or is it more like a smaller amount of content?
It is a smaller amount of content, I would say. Yeah.
How long did the people work on it for?
So for this minimum viable prototype that we created 3 modules, and it took a time period of almost about 3 to 4 months to create the assets and the environment.
And how long did the students work on it for? Was it like a multi-day experience for them, or was it a single instance where they were trying to
Okay.
find?
So do you mean like the users who used the study?
Yeah.
So it was okay. That was just for like a period of 1 hour where they utilized and we were more interested to learn about the user experience and immediate skill acquisition. But for long-term skill acquisition, I think we would have to do a long-term exposure of such content to users.
You're sort of the proof of concept.
Yeah.
Hand it off.
Yeah.
So, last question, I promise.
Yes, of course.
So if I want to compare the part that you did, maybe with existing session by a company for the same class. So what would be the advantage and like a fair comparison between a custom-based welding class and if I buy this one from a company, for example?
Again,
what would be the advantage?
What would be the advantage of VR?
Yeah, or maybe the pros and cons.
Oh, pros and cons.
Yeah, between what you did and an existing class, like I would buy it from a company with maybe a subscription of $20. So what would be the pros and cons? Like, is this yours can be easily modified, customized? Like, what would be the advantage?
Yeah, so like the conventional creation of these kind of simulators, so there is a major cons. Like although like this immersive technology might attract students, they might be interested to learn about the skill just because of the nature of the content, right? It is fun. It is like it tickles your like sensations in a different way as compared to 2D alternatives. But like the major cons is these kind of content are very rigid. Like instructors are not able to tailor it to their class requirements. So that's where like we are planning to provide some authoring capabilities to users. So this simulator, like this particular simulator is kind of rigid. Like you build it once and then you have to use it. It cannot be customized for your class requirements. But like and to
The one we did, you cannot customize it, or the one we buy? Which one is you cannot customize?
like the one we built initially, the first project, we like updated it like later on to make it somewhat customizable.
Yeah, so the author can
Mhm.
customize it, right?
Yes, the author can customize it. Yeah. Mhm.
Any other questions for Dr.
I think, did Dr. Luco on the Zoom have a question?
Okay. Do I have access to the question?
I don't know.
Okay, I can come there.
It's not in the chat. Dr. Luco, did you have a question?
Hello, can you hear me here?
Okay, try one more.
Hello?
Yep, we can hear you.
Okay. Yes, my question is just very general about the smart manufacturing. We are seeing a lot of advantages that this one is going to bring to manufacturing industry. Do you foresee any obstacle to the advancement of this area of technology? Any obstacle?
Do you see any obstacles in general in adopting something like this in smart technology?
Yeah, I think like where the manufacturing is headed is like more interdisciplinary in nature, and
Mhm.
like creating creating content for conventional manufacturing is still, I would say, uh, a little bit easier as compared to like creating content for advanced manufacturing, which integrates a lot of technologies, and like even like AR, VR, XR are a part of those technologies. So that is one thing that I could see, and like the modern manufacturing, it is more data driven in nature. So you have to like account to collect the data in real time, and there is like huge amount of data to be collected and to be analyzed. So I think like those are some challenges that I think uh, exist in creating immersive content for training advanced manufacturing skills.
Thank you.
Yeah.
Let's thank Dr.
Thank you.